right, with the end of that song, I guess it's time to start. All right, okay. Let's see. So last time, not yesterday, but 2 days ago, we left off with chapter 16, which was the scanner. Scanning on demand, it was called. You can see from here, without having to look. And today we're going to work on compiling expressions. And then after we've done that, or at least done as far as we can go, there we go. We're going to work on cleaning up the error messaging coming out of the JLOX interpreter we wrote last time. All right, so compiling expressions. Let's dive right in. This chapter is exciting for not one, not two, but three reasons. First, it provides the final segment of our VM's execution pipeline. Once in place, we can plumb the user's source code from scanning all the way through to executing it. So we did this part. We sort of did some of this part, and now we're going to do this part. Second, we get to write an actual honest-to-God compiler. It parses source code and outputs a low-level series of binary instructions. Sure, it's bytecode and not some chip's native instruction set, but it's way closer to the metal than JLOX was. We're about to be real language hackers. Bytecode was good enough for Nicholas Wirth, and no one questions his street cred. That's right. Third, and finally, I get to show you one of my absolute favorite algorithms, Von Pratt's top-down operator precedence parsing. It's the most elegant way I know to parse expressions. It gracefully handles prefix operators, postfix, infix, mixfix, any kind of fix you got. It deals with precedence and associativity without breaking a sweat. I love it. Pratt parsers are sort of an oral tradition in the industry. No compiler or language book I've read teaches them. Academia is very focused on generated parsers, and Pratt's technique is for handwritten ones, so it gets overlooked. But in production compilers where hand-rolled parsers are common, you'd be surprised how many people know it. Ask where they learned it, and it's always, oh, I worked on this compiler years ago, and my coworker said they took it from this old front-end... ... As usual, before we get to the fun stuff, we've got some preliminaries to work through. You have to eat your vegetables before you get dessert. First, let's stitch that temporary scaffolding we wrote for testing the scanner and replace it with something more useful. So this is in VM. This is our old loop in interpret. Oh, this is the temporary scaffolding? Okay. We still need to create a compiler, right? That's how we call this business. I guess now compile is going to return a Boolean. Oh, right now we have compiler compile source. So instead of doing this, we're not going to pass in the source anymore. We're going to pass in a chunk. Or we're going to get back a chunk. I see. Should we just return it then? I'm trying to think about, what's the best way to do it in Rust. We can just say let chunk equals compiler source. We can still do that and just have it return a chunk. Oh, I see, but we need to determine whether it's got a result, and that's easy enough to do, right? We can just say that a result. Oh. Of course, we're going to have to change our main to handle that, right? That way it can return an error or it can return an OK chunk, right? And we don't have to worry about free because we're in Rust and we don't need to deal with that. Then we're going to set the VM up to run the chunk. And then it's going to run and return an interpret result. So I think interpret result just needs to be this. We don't need an OK anymore. We can just return OK this way. Actually, no, we're going to return a result from the VM. So we're going to say self run chunk. And we don't need to worry about freeing it. Nope, no semicolon. And then this guy, result either nothing or interpret result. Right, and down here at the bottom, This loops forever. Oh, here it is. Return interpret result okay. So this just gets return okay, like that. Yeah, I think that's it. I think that does it. And then in main, we're going to have to handle the results here from interpret. Which we kind of don't do. We just assign it there and ignore the result. Here, there is no, I guess we can say error here. Like that. Does this check? Does not. Okay, cannot be like this. And then compiler currently does not return a interpret result, so result interpret results. And then down at the end of the loop, it's going to have to return okay. Oh, we don't have, oh, that comes out of the VM. So then it should be part of, I guess we're going to need it in main. Let's make it part of main. That way it's accessible everywhere. Nope, of course not. Use create star. What's the right way to do this? We have this, and then we say self. That, and then like that. No. I still can't find interpret result. Oh, create as name. Create root imports are not explicitly named. Okay, so we don't do self here. And then interpret result. Use superstar. There we go. I think that's closer. Expected chunk found this. Oh, because compile, no. Oh, right. Compiler needs to return the chunk. So it's either a chunk or an interpret result. And right now it's not returning a chunk. So this is what we need to change. Okay. I think we're getting close. Chunk new. Let's just do that just to get it to compile. There. We have 8 warnings because we're not doing a bunch of stuff. Right? Free. Right? Opcode. Oh, yeah, because we're not generating chunks yet. Okay, so I think we're done, right? So we have the compiler. We call compile source. We get back the chunk. If we get an error, we throw away the chunk. We don't actually get the chunk. We just return the interpret result of a compile error, which is going to be something that a compiler has to throw. Then we run the chunk. VM IP chunk code. So does run set the IP? No, it doesn't. But what we can set the IP ourselves, right? Because we have a mutable reference to self. So we can just say self IP equals 0 and then run the chunk. Get back the result, and it's either going to be an OK or it's going to be an interpret result, which is going to be the runtime error. All right, so compile takes constant char source and returns a chunk as a bool, but we're handling that with the Rust's result type. That works. That called init scanner is the only line that survives this chapter. All right, so let's just do this. Quick check. We'll go back to the compiler, and I guess we blow away everything else. We do need to set the line, though, don't we? I guess not. I guess all this goes away. So we can replace all those lines with a call to advance, expression, and then consume. Self-advance, self-expression, and I think this is where we need to do this, right? And then self-consume, token type, This one worked with interpret result and use create star. Why did I have to do a superstar here? All right. And why do I need to do it at all? Maybe I should put it in its own error file instead of just throwing it in main. All right, let me get this working. I think I have to use token, right? I don't have token. Oh, it's in chunk. Use create chunk star. Right, and then token type EOF, expect end of expression. And then we're going to just return chunk new. Right, we don't have advance, we don't have expression, and we don't have consume. So, the call to advance primes the pump on the scanner. We'll see what it does soon. Then we parse a single expression. We aren't going to do statements yet, so that's the only subset of the grammar we support. We'll revisit this when we add statements in a few chapters. After we compile the expression, we should be at the end of the source code, so we check for the Sentinel EOF token. We're going to spend the rest of the chapter making this function work, especially that little expression call. Normally we dive right into that function definition and work our way through the implementation from the top to bottom. This chapter is different. Pratt's parsing technique is remarkably simple once you've all loaded in your head, but it's a little tricky to break into bite-sized pieces. It's recursive, of course, which is part of the problem, but it also relies on a big table of data. As we build up the algorithm, that table grows additional columns. If this chapter isn't clicking with you and you like another take on the concept, I wrote an article that teaches the same algorithm but using Java and object-oriented style. Pratt parsing, expression parsing made easy. Alright, I don't want to revisit 40-something lines of code each time we extend the table, so we're going to work our way into the core of the parser from the outside and cover all of the surrounding bits before we get to the juicy center. This will require a little more patience and mental scratch space than most chapters, but it's the best I could do. Single pass compilation. Alright, a compiler has roughly two jobs. It parses the user's source code to understand what it means, then it takes that knowledge and outputs low-level instructions that produce the same semantics. Many languages split those two roles into two separate passes in the implementation. The parser produces an AST, and then the code generator traverses the AST and outputs target code. In fact, most sophisticated optimizing compilers have a heck of a lot more than two passes, determining not just what optimization passes to have, but how to order them to squeeze the most performance out of the compiler, since optimizations often interact in complex ways, is somewhere between an open area of research and a dark art. In CLOX, we're taking an old school approach and merging these two passes into one. Back in the day, language hackers did this because computers literally didn't have enough memory to store an entire source file's AST. We're doing it because it keeps our compiler simpler, which is a real asset when programming in C. Single-pass compilers like we're going to build don't work well for all languages. Since the compiler has only a peephole view into the user's program while generating code, the language must be designed such that you don't need much surrounding context to understand a piece of syntax. Fortunately, tiny dynamically typed LOX is well suited to that. Not that this should come as much of a surprise, I did design the language specifically for this book after all. What it means in practical terms is that our compiler, C module, has functionality you'll recognize from JLOX for parsing, consuming tokens, matching expected token types, etc., and it also has functions for code gen, emitting bytecode and adding constants to the destination chunk, and it means I'll be using parsing and compiling interchangeably throughout this and later chapters. We'll build the parsing and code generation halves first, and then we'll stitch them together with the code in the middle that uses Pratt's technique to parse LOX's particular grammar and output the right bytecode. Alright, so we're going to get into parsing tokens. We're going to actually do something here. I'm wondering what we're going to do with this chunk bitness, because we might have to be passing it into every... This isn't... So we have parser.previous. So this is a global parser. Oh, here it is. All right, So then what's the compiler? I don't know. Okay, so we'll say pub struct parser. It's going to have a current token and a previous token. Oops. And we're going to have a parser in self, I guess. That's going to be mutable because we need to be able to mutate it. Parser colon parser. Like we did in most other modules, we'll have a single global variable, the struct type, so we don't need to pass the state around from function to function. Okay, yeah. So we're gonna have in the compiler, we're gonna have the self, which will have the parser. So that's going to be the equivalent. Advance is going to take a mutable reference to self. And it's going to say parser.previous is parser.current. We're going to have to initialize it with something, though. Do I have to invent a token none or something like that? Just to initialize it with something? I don't want to make this an option because we only needed an option at the beginning. Oops, where's our token type? It's not in chunk. It's in scanner. Okay, so it should probably be pulled out of scanner then. All right, we have this token and token type, and let's create a new file called token, which contains pub struct token and the token type. And then we can just use it here. Use create token star, and then mod token. Okay, and then this can go away. Okay, so now we can say use create token here. We already had the scanner pulled in, but it just seemed cleaner to have it as a token. And then token. Maybe an uninitialized, or I don't know what would be good. Undefined. Let's say undefined for this, and that way when we create this, we'll just, the new token is going to be this, undefined with an empty string and a 0 for a line number. Should I do it that way? Oh, I mean, not here. Here. I do want to have a default token. Enable default for token. Oops, like this, and then fn default, which is gonna just return self, and then self type is token type undefined, Maxime string new, and then line 0. Is that right? Oh yeah, my compiler is still broken here. So let's comment this out. Oh, token default, and then previous. Oh, I put it in the wrong. Oh, parser. Duh. Undefined. Trisma. Hi, hello. How are you? Sorry I missed your greeting there. Cannot borrow is mutable. Oh yes, this has to be mutable. Okay. Okay, 73 errors. Nice. And that's probably all of the tokens that we're not using. Okay, so this is kind of set up. Kind of, sort of. Let's take a look at the compiler again. So we have a parser, and I probably should have a parser default, right? I can derive default and just say parser default here. X. There we go. Yeah, that works. I'm very well, thanks, Trispa. Just trying to get this this stuff ported up from C to Rust. I thought it would go a little smoother because C is closer to Rust than Java is. It's smoother than the first part of this book because we were translating Java to Rust, but this is becoming an interesting programming exercise. All right, so now we can write advance, right? So we say fun advance self, and advance, I guess, doesn't. Oh, we do have error at current. And what does that do? Because it returns void, but it must set some sort of error. Let me take a quick peek ahead and see if we. Yeah, here's error at current, which calls error at. Error at is this, which sets had error to true on the parser. So I guess we could do that, right? And hopefully bool gets initialized to false by default. And then if we had an error, do we have to do it that way, or can we just return the error code? All right, so let's keep working at it this way. So what does advance do? Advance does a loop. Oh, first, yes, we have to set parser self, parser current, previous is self parser current. So we copy that, and then we go into loop. Self parser current is equal to self scan token. Oh, we have to call the scanner's scan token. That's from here, right? Yeah, here's scan token. So the scanner has to be part of the compiler as well. Scanner. So, oh, and then we have to pass in this. This is interesting. How are we going to get this to work? I guess we can just reassign it, right? We can just say self scanner equals that. And the scanner can just be a scanner new without a string. Like that. And then scan token, self scanner, scan token. This is kind of awkward. I'm gonna have to rethink this, aren't I? And then we can say if self.parser.current.ttype is not equal to token type error, break, and then we call self error at current. Parser current start. Oh, not start, Lexeme. And that's advance. This seems really, really awkward. There's got to be a better approach to this, right? Just like in JLox, it zips forward through the token stream. It asks the scanner for the next token and stores it for later use. Before doing that, it takes the old current token and stashes it in the previous field. That will come in handy later, so we can get at the Lexeme after we match a token. The code to read the next token is wrapped in a loop. Remember, CLox's scanner doesn't report lexical errors. Instead, it creates a special error token and leaves it up to the parser to report them. We do that here. We keep looping, reading tokens, and reporting the errors until we hit a non-error one, or reach the end. That way, the rest of the parser sees only valid tokens. The current and previous token are all stored in this struct, so we already have that. Like we did in other modules, we have a single global variable of this struct type, so we don't need to pass the state around from function to function in the compiler. Okay. If the scanner hands us an error token, we need to actually tell the user. That happens using this. So there's error current. I'm assuming it doesn't need a mutable reference to self. Self error at self parser current. I guess we could do that. And then a message. Oh, this takes a message. Message stir. Was there a message up there? I just missed it. Oh, yeah. Parser current lexeme. I guess this would have to be ampersand, right? Okay. So that's all that is. And then we have, we pull the location out of the current token in order to tell the user where the error occurred and forward it to error at. More often we'll report an error at the location of the token we just consumed, so we give a shorter name to this other function. fn error self message stir self error at self parser previous message. Okay. And then we're going to have to write error at, and that's the big one. Error at self message. Oh, not self message. Token. Token message stir. So eprint bang line this error and then token.line if token.ttype is equal to token type EOF eprint at n else if token t-type is token type error eprint nothing else eprint bang space at, and this is the length and the right, and so we don't need to do that in Rust because we just say token.lexeme. And then ePrintln colon message. Oh, but that's a stir, so you can't just print it out directly. And then self parser had error is true. Let's see what blows up. Oh, self. Println is not a function. That is true. It's a macro. And so how do we do this? Expected string. I guess I can just say toString. Still doesn't like that, so I gotta ampersand it. There we go. Move occurs because, right, so that's what we're trying to do, is just copy the token over. Can I implement copy? We don't have this here yet. Copy me. Oh, because I have a string in it. Okay. So what do we want to do here? Because we do want to save the previous We can't do the move. Oh, where does this need to be mutable? Oh yeah, error needs to be mutable all the way down because we're setting parser error. I guess we could use a ref cell to avoid that issue. What are the other errors? Can't borrow self as mutable, blah, 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 right? So, let message equal this, and then we can just say message. Right, so, oh, we still have 4 errors. It doesn't like this. Why? Oh. I guess we'll go with cell, ref cell. And that allows us to make this a ref cell, a bool. And that means we can't derive default anymore, right? Well, maybe we can. And then errors don't need to be this, or this, or this, but we can say self parser had error and replace true. Let's see if that works. Yeah, okay, so now we're down to just this one error about copying the token. And so I can just say previous t-type is equal to current t-type, self parser previous lexeme is equal to self parser current lexeme clone, and then self parser previous line equals self parser current, or I could just implement copy. Why don't I implement copy? Can I do that? Or do you implement clone and then it derives copy? I can't remember now. Let's find out. This does not implement copy. But we can implement clone, right? And then derive copy. Fn clone, self. I think that's the way it works. And then just say self t-type is self t-type. Lexeme is self lexeme clone. And then line is self line. Right? And this move occurs. Oh, can't move out of parser current, which is behind a mutable reference. So I can just clone it, right? Yeah. Okay. Done. Now we're down to 10 errors, 10 warnings. Really? Why aren't we complaining about all of the tokens that aren't being used? That's strange. Okay, not going to worry about it. But we got this working, or at least we got this compiling. Be nice to have tests. Okay, so this was the error stuff. We have the had error, and I kind of working my way around the mutable self thing by using a ref cell to set the had error. And then when we do this, we're going to say return not parser had error. So then we're going to do down here, after we're done with all of this, if self parser had error, how do you get it out of the cell? You just deref it. Then error interpret results, compile error, else. Okay, chunk new. And we'll pass a real Ripcell can't. Oh, borrow. It's called borrow. I forgot. There. I remembered the start part and I forgot the borrow part. I've got another flag to introduce for error handling. We want to avoid error cascades. If the user has a mistake in their code and the parser gets confused about where it is in the grammar, we don't want to spew out a whole pile of meaningless knock-on errors after the first one. We fixed that in JLock using panic mode error recovery. In Java Interpreter, we threw an exception to unwind out of all the parser code to a point where we could skip tokens and resynchronize. We don't have exceptions in C. Instead, we'll do a little smoke and mirrors. We add a flag to track whether we're currently in panic mode. There is set jump and long jump, but I'd rather not go there. Those make it too easy to leak memory, forgot to maintain invariants, or otherwise have a very bad day. Agreed. Okay, so I guess we'll do the same thing here. Panic mode, cell. Although, in Rust we do have results that we could use instead. So let's do it with the panic mode thing, and then maybe we can refactor panic mode out and just return results. So in error at, the very first thing we're going to do is self parser panic mode replace true. After that, we'll go ahead and keep compiling as normal as if the error had never occurred. The bytecode will never get executed, so it's harmless to keep on trucking. The trick is that while the panic mode flag is set, we simply suppress any other errors that get detected. Oh, okay, so we'll check right here. If self parser panic mode borrow return. So we only ever call this once. So what's this doing then? Because the first time we call this, panic mode gets set, and the second time we call it, we can just use panic mode as, okay. I guess we'll get there. There's a good chance the parser will go off into the weeds, but the user won't know because the error all gets swallowed. Panic mode ends when the parser reaches a synchronization point. For locks, we choose statement boundaries so that when we later add those to our compiler, we'll clear the flag there. So we initialize the new fields. I did that already in the default constructor, standard lib, and now we're going to write consume. That's our next. So I guess we're going to save expression for last. Okay, so I was saying put it after advance. I'll put it after advance. fn consume self, and then it's going to take a t-type of token type and then a message of stir, and doesn't return anything. If self parser current t-type is equal to t-type, then we're going to call self advance and return. Otherwise, we call self error at current. Can we get away with this now? Let's find out. Oh, it's just message. Yeah, we don't. I was getting ahead of myself there. Okay. That's even easier. It's similar to advanced in that it reads the next token, but also validates that the token has an expected type. If not, it reports an error. This function is the foundation of most syntax errors in the compiler. Okay, that's enough on the front end for now. All right, does this build? It does. All right, emitting bytecode. After we parse and understand a piece of the user's program, the next step is to translate that to a series of bytecode instructions. It starts with the easiest possible step, appending a single byte to the chunk. So this is a compiler. I'm going to call emit byte write chunk. So, and then we have this thing called current chunk, which I think we have in our struct, right? We don't have it. Okay, so that's going to be something we need to add, right? means down here, we say chunk, this chunk, new. And then I guess we're going to just return that part here. Can we do that? Is that going to work, or is that going to blow up saying we can't return that? Move occurs because self-chunk has type chunk, which does not implement the copy trait. Yeah, I don't want to copy the chunk. Maybe then what we need to do is this. There's a source string, and then I guess you can say chunk is a mutable reference to chunk. And what do we do here? Because I don't want to have to pass it down everywhere. I don't want to pass it around. Now, if we make this a reference to a chunk, then we have to start adding lifetimes. Is that going to hurt us? How bad is that going to hurt? Oh, oh, okay, so we have to actually pass it in here when we create the new chunk. Right? And we don't need to return this anymore. Oh, the compiler needs... Wait, how is this blowing up all of a sudden? Compiler new. Oh, now needs a chunk. To compile. So we have to say let ma chunk equals chunk new, and then compiler let chunk, and we no longer return it, we just compile source and return good or bad. Okay, this seems to do the trick, and now we have access to a chunk reference, so it's not as bad as I thought it was going to be. So now we can do this emit byte business here. And right after consume it says, so fn emit byte, not self. All these functions returning void. So self.chunk.write. Now we have a difference between write opcodes and write U8s, right? Yeah, we have a write and we have a write opcode. So if we take in this byte as U8, we can say self chunk write byte, and we need the current line, which is self parser previous line. That's not called anywhere, but let's see if it compiles. Nope. Oh, but I have a mutable reference. Okay. Let's try it. See if it blows up. Okay, that worked. That worked. Okay. After we parse and understand a piece of the user's program, the next step is to translate that to a series of bytecode instructions. Hey, Supercuber, how are you? It starts with the easiest possible step, appending a single byte to the chunk, right? And the difference is that I need a different thing to write or write opcode. So I'm probably going to need an emit opcode as well. But when we get there, we'll see. It's hard to believe great things will flow through such a simple function. It writes the given byte, which may be an opcode or an operand to an instruction, right? Okay. If it's an operand, it's a byte. That's easy. If it's an opcode, we're going to have to do it this way. because we don't do polymorphism in Rust. The chunk that we're writing gets passed into compile, but needs to make its way to emit byte. To do that, we rely on this intermediary function. And we do have this into business. I don't know if there's an easy way to... All right. What's the intermediary function? This current chunk. Oh, okay. Yeah, we don't need to do that here because our intermediary function, we have the compiling chunk as part of the compiler. Supercuber says, I actually wrote a macro to convert a struct with variants like constant U8 into bytes and append that to the chunk. It was pretty fun to learn how to write derived macros. That's not a bad idea. Actually, but so what I want to do, and maybe this is getting ahead of myself, if I take a look at our token, well, I can't. Oh no, not the token. Where is it? Is it in the VM? Where's our instruction set? Huh. Somewhere we have instructions like op return. Yeah. So what I was thinking was that these, instead of just being an enum that we switch back and forth on, is that actually they would take the operands, right? So we'd have opcode add, and then it would take two U8s. Actually, add doesn't take any arguments. It just uses the stack, right? But constant does. So constant could have a U8 in there, which is which is exactly what you wrote in the in chat. Yeah. All right. Well, I'm gonna keep barreling on this way and see how broken it makes my brain. So with the compiling chunk is already stored here in the compiler. Right now, the chunk pointer is stored in a module level variable like we store other global state, right? Which is what I'm trying to avoid with this port. Later, we'll start compiling user-defined functions. I mean, I could use lazy static everywhere, but that would, yeah, that's not rusty. I mean, this already isn't very rusty, but that would be even less rusty. To avoid having to go back and change a lot of code, I encapsulate the logic in current chunk. Okay. And then we initialize compiling chunk there. Okay. Not something we need to do because I just did all of that. End compiler. Emit return. Okay. So after we do the consume, we call end compiler. Self end compiler. I don't know why we can't just do this there. Maybe there's some more wrap up that needs to happen when we end the compiler. All right, so after emit byte, and it should be end compilation, right? Emit return, self emit return, which is yet another function, right? And then we're going to add that after emit byte, fn emit return, not self. And this is self chunk, and this is where we say write opcode return. While we're here in the back end, we may as well make our lives easier. Here's emit bytes, plural. Oh, we need the line number, of course. Does emit byte already? Oh, so what I want is an emit opcode then, or an emit. Yeah, if I call emit byte here, self emit byte, opcode return into. Yeah, that works. Okay, and that way we get the line number through this guy here. We have emit bytes, plural. Over time, we have enough cases where we need to write an opcode file, a 1-byte operand. That's what defining this convenience function. All right, so if that's going to always be opcode file by operand, that's not too bad. Emit bytes, we can say self byte 1 is going to be the opcode byte 2 is going to be U8. Self emit byte 1 and 2. Self emit byte 2. Okay. It doesn't complain about that. And say, okay, now we're getting to parsing prefix expressions. How are we doing on time? Oh, it's not even 8. Okay. We've assembled our parsing and code generation utility functions. The missing piece is the code in the middle that connects those together. The only step in compile we've left to implement is this function, expression, after end compile. Okay. I'm going to assume that it's going to take immutable self. What goes here? We aren't ready to implement every kind of expression in locks yet. Heck, we don't even have booleans. For this chapter, excuse me, for this chapter, we're only going to worry about 4 number literals, parentheses for grouping, unary negation, and the 4 horsemen of the arithmetic. Which I think we have all but parentheses right now in the VM. And we don't even need them in the VM because that's a compiler thing about how things get pushed onto the stack. Okay. As we work through the functions to compile each of these kinds of expressions, we'll also assemble the requirements for the table-driven parser that calls them. All right, parsers for tokens. For now, let's focus on the locks expressions that are each only a single token. In this chapter, that's just number literals, but there will be more later. Here's how we can compile them. We map each token type to a different kind of expression. We define a function for each expression that outputs the appropriate bytecode. Then we build an array of function pointers. The indexes in the array correspond to the token type enum values. Ooh, that's going to be an issue, isn't it? And the function at each indexes the code to compile an expression of that token type. I guess we can just use a match then. To compile number literals, we store a pointer to the following function in the token number index in the array. Where's this array? Where's this alleged array? I'm just going to scan forward. There's precedence. I'm not seeing the array. So basically, oh, here it is. Here it is. Okay. So for each token type, we have 3 different things. We have the grouping, unary or binary, or number, which is the function to parse it, the type of expression it is, which is binary. And we had something similar in JLOCs to this, and then the precedence for each one. And most of them, the default is just null, prec none. So we can just create a match routine that returns a tuple of these 3. I think that would be the easiest way to do this. And we can just make a function called rules, which returns that parse rule. All right, so let's go all the way back. But it seems like there's going to be a lot of work before we even get there. All right, so here's number. Static void number. Double value, string to decimal. So the way this is going to work, so this is after end compiler. Fn, number, itself. And this is just going to take the lexeme and parse it into a string to decimal. No. Oh, is this? I think this is the pointer to the end of the string, which we don't need because we already have that length in there. End pointer. Yeah, it's just the end pointer. Okay. So I'm not going to worry about that because Rust will parse this for us. We can just say let value f64. Actually, we don't have to do that, right? We can say let value equals parse self parser previous and then parse colon f64. Is that the format? Oh no, you have to method not found, lexeme parse. There we go. Okay, and then we can just emit constant value, self emit constant. value. And now, of course, we need emit constant, which comes after emit return. Fn emit constant. Value. Oh, which is a value. Which I think I can. Can I value this? Because value is an F64. Where is value? It's in value. Who knew? So we're just going to unwrap this and assume it works. We're going to assume that we parsed a F64 value correctly. Okay, fair enough. We assume the token for the number literal has already been consumed in this stored in previous. We take that lexeme and use the C standard library to convert it into a double value. Then we generate the code to load that value using this function. Yeah, so if this unwrap fails, there's a bug in our compiler rather than a bug in the locks user's source code. All right, so now we're going to emit bytes. Self emit bytes. Byte 1 is going to be opcode constant, and byte 2 is going to be make constant value. And where does that come from? Chunk. Oh, that comes from here. We call the current chunks add constant. Got it. Okay. So can we do that here? Self make constant. Oh, that's going to be a problem, right? Because we're going to be passing this. Let's do this in two expressions here. Let constant equals self make constant value. And then we can just say constant here. And then we're going to have to write make constant. First we add the value to the constant table, then we emit an op constant instruction that pushes it onto the stack at runtime. To insert an entry in the constant table, we rely on this. And this is right after emit return. So our constant is equal to self.chunk.add constant value. If constant is greater than U8 int max, then too many constants in one chunk. Oh, we don't want to blow up, right? So right now I think add constant returns a U8 when it should return a results type of U8 or too many. Right? Because we have self-constants right. And self-constants right is this value array, which returns a U size, right? Yeah, it returns a U size. So we have to say here, we have to check. So this is going to be a result of U8 or stir. Sure. Let IDX equals this. If IDX is greater than, oh, is there a U8 max macro? Like max? Something like that? Rust. Integer max. Yeah, standard U32 max. So we can do the same thing here. Standard U8 max. All over. I guess greater than, right? What do they have in here? Greater than, yeah. Then we're going to say error to, what error should we, I guess we could just return a unit, right? I've never tried that before, but else IDX as U8. Okay. And then back here, nope, back in the compiler, we need to do this business here. We can say like constant equal, or can we say this, match? Okay, constant, then return we need U8 max as U size. Oh, thank you. Thank you, Mizzard. And hello. What was it in values? Oh, it's in value array? No, it's right. Oh, this is, yeah, it was in values. Okay. As U size, like that, right? I can't do it. I can't save it yet. Return constant, and this is going to be error. Anything is going to return, or it's going to generate this error. Self error. Too many constants in one chunk, and then return 0. Actually, we don't need the return statements. All right, let's see if this blows up. Oh, U8 : try from. And what does that return? Finds either a U8 or a U8 as try from error. Okay, that's even better because all I have to do is that one thing, right? No, I keep going there. Source chunk. All right, I can just say IDX. Oh, this is try from U32. That's fine. There's a try from U size, right? Somewhere? I have try from I size, try from U size. Try from U size. Yeah, try from U size. Okay. So we can just say IDX. No, U8. IDX. Try from IDX, like that. And then do I have to... It's either going to be a U8 or it's going to be this try from U8 business. Do I have to import... It says unstable? What does unstable mean? That doesn't work? What do I put in here? It's probably just a macro. Yep, it's just a macro. I mean, do I have to like import? Create num try from int error. Hi Zeta Numbers, how are you? Oh, there's something called .map error. I missed that part. What's that? Maps result TE to result TF, applying function to convert it. I don't know what that does. Oh, Zeta Numbers has the answer right there. Map error, whatever, into just nothing. Oh, map error. All right, let's see what blows up. Oh, look at that. It works. Thank you, guys. Thank you, everyone. All right, so this returns either the constant or reports an error and returns 0. And it doesn't matter that we're returning 0 because we're going to error out anyway, and we're not going to run the code. All right, so most of the work happens in add constant, which we defined back in the earlier chapter. This adds a given value to the end of the chunks constant table and returns its index. The new function's job is mostly to make sure we don't have too many constants. Since op constant instruction uses a single byte for the index operand, we can store and load up only up to 256 constants in a chunk. Yes, that limit's pretty low. If we were a full-size language implementation, we'd want to add another instruction like op constant 16 that stores the index as a 2-byte operand. Code to support that isn't particularly illuminating, so I omitted it from CLOCs, but you'll want your VMs to scale to larger programs. And that's basically all it takes. Provided there is some suitable code that consumes a token number token, looks up number in the function pointer array, and then calls it, we can now compile a number of literals to bytecode. All right, so we're done with this part, but we're not even close to being able to do this because we don't have the function pointer array, because that's way far down. Z number suggests perhaps we could use an option instead. Yeah, I mean, why not? Let's go. Right, because we don't need to. If this returns an option U8, right? Then if the try from fails, then we'd have to map. We'd have to map error to none. But we'd have to map the whole thing to a sum if it succeeds. Just okay it? Oh, so okay converts a result to an option? Yes, it does. Okay. And then this has to change, obviously. And we can say if let some constant equal this, then just constant. Else. Is that cleaner? Sure. All right, let's go with that. I like it. Learned something new. I didn't know OK converted a result into an option for you. That's nice. And then we don't have to do a map error, right? Oh, SuperKeyboard just said that. Yeah, we can just directly map it that way. Okay. And then I can get rid of this comment. Very good. All right. So we did that. Parentheses for grouping. Our as yet imaginary array of parsing function pointers would be great if every expression was only a single token long. Alas, most are longer. However, many expressions start with a particular token. We call these prefix expressions. For example, when we're parsing an expression and the current token is open paren, we know we must be looking at a parenthesized grouping expression. It turns out our function pointer array handles those too. The parsing function for an expression type can consume any additional tokens that it wants to, just like in a regular recursive descent parser. Here's how parentheses work. So we have grouping. So after end compiler, we're going to add grouping, which is called self-expression, and then self-consume, token type, right paren, expect, right paren after expression. Okay. Again, we assume the initial open paren has been already consumed. We recursively call back into expression to compile the expression between the parentheses, then parse the closing paren at the end. A pret parser isn't a recursive descent parser, but it's still recursive. That's to be expected since the grammar itself is recursive. As far as the back end is concerned, there's literally nothing to a grouping expression. Its sole function is syntactic. It lets you insert a lower precedence expression where a higher precedence is expected. Thus, it has no runtime semantics on its own and therefore doesn't emit any bytecode. The inner call to expression takes care of generating bytecode for the expression inside the parentheses. Okay, that makes sense. Unary negation. Unary minus is also a prefix expression, so it works with our model too. So we're going to create a function called unary, and adding it after number. So unary let operator type is equal to self parser previous t type. We'll compile the expression, and then we look at the type. If it's a minus, then we emit a negate, and then we return. Otherwise, we return. The leading minus token has been consumed as and is sitting in parser previous. We grab the token type from that to note which unary. I'm guessing this is going to expand this switch statement. Otherwise, why do it this way instead of just with an if? We grab the token type from that to note which unary operator we're dealing with. It's unnecessary right now, but this will make more sense when we use the same function to compile the bang operator. Okay. As in grouping, we recursively call expression and compile the operand. After that, we emit the bytecode to perform the negation. It might seem a little weird to write the negate instruction after the operand's bytecode since the negative appears on the left, but think about it in terms of the order of execution. Yeah, it's a stack-based, so it makes sense to negate the expression after the expression's been evaluated. We evaluate the operand first, which leaves its value on the stack, then we pop that value and negate it and push the result. Right, that's exactly it. So the op negate instruction should be emitted last. This is part of the compiler's job. All right, so all we need to do, right now I'm just going to say if, and then we can switch it to a match later. Operator type equal token type minus self emit byte op code negate into else unimplemented. Nope. All right, that compiles. Supercuber says, interesting, that means we cannot have a negative constant, only a positive constant that is negated at runtime. Yeah, that's right. The number in the scanner code, we can take a quick look. Where we look at number, if we see a negative sign, we go to minus. If we see a number, then we parse the number. So we never have minus signs inside numbers. And right now, at least, I don't know if we'll extend it later, but right now our number only looks for digits and the decimal point. It doesn't look for, like, you can't write 12.4E27, for example. It doesn't look for scientific notation style numbers. Okay. Emitting the opt-negate instruction after the operand does mean that the current token when the bytecode is written is not the minus token. That mostly doesn't matter except that we use that token for the line number to associate with that instruction. That means if you have a multi-line negation expression like print minus true, then the runtime error will be reported on the wrong line. Here it would show that the error is on line 2 even though the minus is on line 1. A more robust approach would be to store the token's line before compiling the operand and then pass that into emit byte, but I wanted to keep this thing simple for the book. I don't think that's too much of a big deal, right? If the error is here, I mean, whenever you see error messages, you're always looking at the surrounding context, so I don't think it's that big of a deal. There's one problem with this code though. The expression function it calls will parse any expression for the operand regardless of the precedence. Once we add binary operators and other syntax, that will do the wrong thing. Consider negative a.b plus c. Here the operand to negative should just be the a.b expression, not the entire a.b plus c. But if unary calls expression, the latter will happily chew through all of the remaining code, including the plus. It will erroneously treat the minus as lower precedence than the plus. When parsing the operand to unary minus, we need to compile only expressions at a certain precedence level or higher. In JLox's recursive descent parser, we accomplish that by calling into the parsing method for the lowest precedence expression that we wanted to allow, in this case, call. Each method for parsing a specific expression also parsed any expressions of higher precedence too, so that included the rest of the precedence table. The parsing functions like number and unary here in CLox are different. Each only parses exactly one type of expression. They don't cascade to include the higher precedence expression types too. We need a different solution, and it looks like this. Parse precedence. So add this to compiler after unary, okay? And then it's going to take, I guess, a self. I don't know if it needs mutable, but let's see. And precedence is going to be precedence. And then it's going to do this. The function, once we implement it, starts at the current token and parses any expression at a given precedence level or higher. We have some other setup to get through before we can write the body of this function, but you can probably guess that it will use that table for parsing function pointers I've been talking about. So right now it doesn't do anything. And we don't have precedence yet. For now, don't worry too much about how it works. In order to take the precedence as a parameter, we define it numerically. Okay, so let's just say enum here. None. Assignment, or, and quality comparison. Term, factor, unary, call, and primary. Okay. These are all of Lox's precedence level in order from lowest to highest. Since C implicitly gives successively larger numbers, didn't mean to do that. I meant to do this and go down here and give us a number so we get numbers here. And maybe we can derive partial equal. So we can compare them. Yep. This means that prec call is numerically larger than prec unary. For example, say the compiler is sitting on a chunk of code like this. If we call parse precedent, prec assignment, then it will parse the entire expression because plus has a higher precedence than an assignment. If instead we call parse precedence prec unary, it will compile a minus b and stop there. It doesn't keep going through the plus because addition, which is term. I probably should comment these out, right? Addition has a lower precedence than unary operators. Equals and bang equals. This and this is plus and minus. Factors are star and division. Unary is just minus. Oh, bang and minus. Call is dot and parens, and primary gets left alone. Okay? With this function in hand, it's a snap to fill in the missing body for expression. Except we haven't written expression yet. Have I? We have a grouping. Or maybe, maybe it had been written before. Yeah, okay, we have it right here. Self. Parse precedence assignment. Ugh. Probably a good candidate for derive ORed in a moment. Oh, yeah. Well, I did partial equal. Maybe it is ORed that we care about. Oops. We need partial ORed. Okay, let's do that and see if we need EQ and ORed itself, then we'll add those two. That's one of the things I like about Rust. You just keep pounding whack-a-mole errors until it compiles. All right. So we simply parse the lowest precedence level, which subsumes all of the higher precedence expressions too. Now to compile the operand for unary expression, we call this new function and limit it to the appropriate level. So in unary, instead of calling self-expression, we call parse precedence with precedence unary. Yeah. We use the unary's operator own precedence unary precedence to permit nested unary expressions like bang bang double negative. Since unary operators have pretty high precedence, that correctly excludes things like binary operators. Speaking of which, not that nesting unary expressions is particularly useful in locks, but other languages let you do it, so we do too. Binary operators are different from the previous expressions because they are infix. With the other expressions, we know what we are parsing from the very first token. With infix expressions, we don't know we're in the middle of a binary operator until after we parsed its left operand and then stumbled into the operator token in the middle. Here's an example, 1 plus 2. Let's walk through trying to compile what we know so far. We call expression, which calls parse precedence assignment. That function, once we implemented, sees the leading number token and recognizes it is parsing a number literal, hands off control to number. Number creates a constant, emits a constant, and returns back to parse precedence. Now what? The call to parse precedence should consume the entire addition expression, so it needs to keep going somehow. Fortunately, the parser is right where we need it to be. Now that we've compiled the leading number expression, the next token is plus. That's the exact token that parse precedence needs to detect that we're in the middle of an infix expression and to realize that the expression we already compiled is actually an operand to that. So this hypothetical array of function pointers doesn't just list functions to parse expressions that start with a given token. Instead, it's a table of function pointers. One column associates prefix parser functions with token types. The second column associates infix parser functions with token types. The function we will use as the infix parser for token plus, minus, star, and slash is this. All right, so static void binary does not take any arguments. So let operator type parser previous t-type. Oh, self parser previous t-type. And then parse rule is get rule. Let rule equal self get rule operator type, and then self parse precedence. Oh, we're gonna have to get the next one in the precedence table. Rule dot precedence plus 1. How do you do that with enums? Rust, enum, previous, and next. How do I toggle? That's not what I'm looking for. I don't want to use a strum crate. is there a way to say right, that's an error. Zero variant enums, variant visibility. But is there a way to say get next? There's enum iterator, which is another crate, which I don't want to use. I don't want to use a crate. Supercuber says, tried looking for successor, predecessor, but I don't think there's such a thing in the standard library. So what I could do is cheat and just say, oops, and press F1 by accident. Okay, what I could do is cheat and say something like let current equals rule dot precedence as usize. Let next equals current plus 1 as precedence. Oh, or I can write an into for precedence, right? I don't want to do that. Can I do that? Because precedence is number based. Let me see if this compiles. What blows up? Get rule doesn't exist. But what I can do is just say precedence, and then get rid of that. Okay, so this is where, an as expression can only be convert. So can I convert a number into a Supercuber says you can't as back into precedence. Rust convert number to enum. And what is this saying? Yeah, you have to do this, which I don't want to have to do. Right? I can write it from. I can write from for it, but then I'd have to match. Yeah. Zeta number says you can mem transmute it. Oh, that sounds like something that I don't even want to go near. Impl from usize for precedence. From. Oh, isn't there? Do you have to put a type in there or something? Let me see what this says. I try to compile it. Let's just copy this, paste it there, and done. Right? Why is that complaining? Oh, because I have type here. Zeta number says it's fine, just use repr on your enum and make sure you're in the range, or increase decrease. Oh, make a next and previous on precedence. Yeah. Can we do that? And that would avoid the whole +1 business. Didn't I put it? Oh, in the wrong. Here it is. So I can just say current, I could just say next is equal to a rule dot next, right? I still want a from, so that I can translate it back and forth, and then I can just say impl precedence on previous self. And then we can just let previous equal self as usize, and then return p plus 1 and 2, P minus 1 and 2. And then Supercuber says, make a copy and just pass by value everywhere. Yeah, I guess that's not a bad idea. And then next is just the same thing, but with plus. Right, and then this just needs to be written. Yeah, I know that matches that closing brace. What am I missing here? Oh, I put this here, duh. Okay, all right, so that works. We just have to do this part. Return type should be at least option. Oh, if we go past the end? If self is primary, none else. Like that. And then if self is, what's the first one? Oh, it should probably be precedence primary. And precedence none. None else. That's going to complicate things down below. Oops, I inserted everything by one. That was bad. Okay, and then blank line between to make me happy. And then this has to be option. And we can unwrap down here. Because if we fail, there's checked sub. Okay. But we're not. The checked sub would work, right? But the checked add wouldn't work because you can definitely add one. Yeah, so this will, Supercuber says panic, and this will panic right here. But we could panic up here. Right? Yeah, let's do that way. No next after primary. And then this doesn't have to be else. Panic. No previous before none. And that way we don't have to unwrap. And expected enum found nothing. Right. Okay, so this is where we need to do this. Match V. 0 is precedence none. Assignment or and equality, comparison term factor, unary call, primary. And default is panic, cannot convert. Oh, I can't do this, can I? Into precedence. I don't think I can do that. I have to put it in a format, right? Oh, what am I doing? 9 and 10. And then assignment or and equality comparison term factor. Did I miss one? Unary call and primary. No, it didn't complain, so far so good. I don't like having to do this though, given the fact that all of these values are values, right? These are all numbers, and we have the ability to compare them. There's got to be something better than this. Oh well. You can replace underscore with v if you feel that shouldn't run. Oh, I see what you're saying. Yeah, just make it a general like this. Although this didn't complain, so that's good. Supercuber says there's nothing better in standard, sadly. Yeah. Well, maybe that'll be like Rust 1.65. We'll work on getting that into the language. Meanwhile, we do this. All right, so that allows us to do precedence, next, and prebs. Oops. Let's go to here, where we were doing some code. Yeah, okay, so now we were going to do get rule, and that was going to contain a parse rule, which we haven't written yet. And so we're going to just say parse rule next. Rule.precedence.next. Like that. That's this line here. Zeta number says there's transmute. Yeah, I really don't want to mess around like that in Rust. I mean, I know it's perfectly valid Rust code, but I'm still too much of a beginner to feel comfortable doing that. Okay, so then we match on operator type. If it's token type plus, then we're going to self-emit byte opcode add into. Then we have minus star and slash, and then everything else is unreachable. Unreachable panic, or let's say to do. Not done yet. Let's just say to do like that. And this becomes minus, and so does this. And this becomes star. Oh, this become minus, it can become subtract. And then this becomes slash, and this becomes multiply, and this becomes divide. I'm hoping I get to a point where I can do something before I run out of time. I'm getting close on the end of my stream time. I got less than 20 minutes left. Ooh, Zeta numbers. Sorry to divert your attention from the code, but what's your experience with unsafe Rust? I have zero experience with unsafe Rust, although I did see, I did read watch John Hu's stream on unsafe Rust, or his YouTube. I don't know how to spell his last name. There he goes. Jengset. That's it. You ignore the G's when pronouncing his name, is the answer. But he has a video on unsafe Rust, or a couple of videos. His crust of Rust things. Unsafe Chronicles. And I did watch some of that. And it was a very interesting thing. I'm sure you've seen it too. But I haven't used any unsafe stuff. Some say it's harder than C's unsafe, but I've read Stacked Borrow's paper and I feel a lot more confident. What's Stacked Borrow's paper? I'm just going to Google exactly what you typed. Oh, Stacked Borrows, an aliasing model for Rust. All right. I will check this out. Thank you for letting me know about that. But yeah, I still don't feel comfortable writing unsafe, because the code, you're declaring it as a human. You're saying, yeah, borrow checker, you think it's unsafe, but I know it's actually safe. And I'm not that confident in Rust to know that. All right, so we have get rule. So this is the only thing we're missing right now is this get rule business. When a prefix parser function is called, the leading token has already been consumed. An infix parser function is even more in medias res. The entire left-hand operand expression has already been compiled and the subsequent infix operator consumed. The fact that the left operand gets compiled first works out fine. It means that at runtime that code gets executed first. When it runs, the value it produces will end up on the stack. That's right where the infix operator is going to need it. Then we come here to binary to handle the rest of the arithmetic operators. This function compiles the right operand, much like how unary compiles its own trailing operand. Finally, it emits the bytecode instruction, that's here, that performs the binary expression. Okay, when run, the VM will execute the left and right operand code in that order, leaving their values on the stack. Then it executes the instruction for the operator. That pops the two values, computes the operation, and pushes the result. The code that probably caught your eye here is the get rule line. Well, it caught my eye only because it doesn't compile. When we parse the right-hand operand, we again need to worry about precedence. Take an expression like 2 times 3 plus 4. When we parse the right operand of the multiply expression, we need to just capture 3 and not 3 plus 4 because plus is lower precedence than star. We could define a separate function for each binary operator. Each would call parse precedence and pass in the correct precedence level for its operand. Zeta Number says, I haven't watched videos about unsafe actually, which I should. Yeah, his videos are really good. He talks about exactly how you define things to be unsafe, and he says, whenever you write unsafe, add a comment explaining to the reader why it is actually safe to do. That way, when you're reading the code, you can verify for yourself whether or not what the code writer assumed to be true is actually true. So each would call parse precedence, pass the correct precedence level for its operand, but that's kind of tedious. Each binary operator's right-hand operand precedence rule is one level higher than its own. We can look that up dynamically with this get rule thing we'll get to soon. Using that, we'll call parse precedence with one level higher than its. Right, so that's what I'm doing here. And it's this operator's level. We use one higher level of precedence for the right operand because binary operators are left associative. Given a series of the same operator like this, we want to parse it like this. That's right. Thus, when parsing the right-hand operand to the first plus, we want to consume the 2, but not the rest. So we'll use one level above plus as precedence. But if our operator was right associative, we would be wrong. Given this, since assignment is right associative, we want to parse it like this. To enable that, we call parse precedence with the same precedence as the current operator. We don't need to track the precedence of a prefix expression starting with the given token because all prefix operators in locks have the same precedence. Okay, so now we get to the Pratt parser. We now have all the pieces and parts of the compiler laid out. We have a function for each grammar production, number, grouping, unary, and binary. We still need to implement parse precedence and get rule. We also need a table that, given token type, lets us find the function to compile a prefix expression starting with the token of that type, the function to compile an infix expression whose left operand is followed by a token of that type, and the precedence of an infix expression that uses that token as an operator. We wrap these 3 properties into a little struct which represents a single row in the parser table. So we have this parse rule thing. So we can toss that at the top. Struct parse rule. We're just going to take a parse function prefix, a parse function infix, and a precedence. And a parse function apparently is just this, but if we're going to do that here, that's going to be a little more complicated than I was anticipating, because if I look at number, or grouping even, let's start with grouping. It does take a mutable reference to self. And can we do that here? Can we say prefix is equal to a function which takes a mut compiler? Trait objects must include the did keyword. Oh. Yeah. Let me comment these 2 lines out. because I think the borrow checker is going to... Oh, the borrow checker did not complain about this? Really? You could just do that? I thought this was unsized, so we don't know... We would have to box it up or something. And then press dense. Use an FN there. You don't need a closure. I'm not sure what you mean. Oh, this thing here? Okay. I like that better. I like that better. I never required... Yeah, FN versus FN. Your struct becomes unsized if it has last field unsized. All right. Well, we're going to... Here's where we create the rules, right? So these are all the parser rules. And this is just going to become, instead of this giant array, we're going to call get rule, which is going to look it up. So this is just going to be a match anyway. So let's make this a match. Let's see if this works. Let's write get rule. Let's comment this back in. Where does get rule supposed to be? After parse precedence? And we still need to write parse precedence, don't we? Yeah, we still need to write parse precedence. Okay. Get rule. Self, and actually we don't need self. This can just be a static function. Oh, well, I mean, we're returning... Okay, let's see what happens. And then token type. Oh, it's not a token, it's a token type. And this is going to return a parse rule. So match t type. And most of these are going to just be null, null, prec, none. So that's going to be our default case. Oh, we can't do null. Ray in the mouse cursor says rust. Yes, not rust the game, but rust the language. So if these are nones, we want these to be options. There. Right? So we want to say none, none. Oh, yeah, none, none, and precedence none. Does that compile? Oh, prefix, infix, precedence. Okay. All right, so that works. Now we just have to write that giant table. Zeta number says box din function should not allocate anything fn when you pass second as first. I'm not smart enough to understand that. I'm not smart enough to understand what you're getting at. Token type left paren is going to return a parse rule with self grouping. Prefix. Will this work? Self grouping. Infix of none and a precedence of precedence none. Will that work? comma? Yeah. It's a method, not a field. I don't want to call it. I want to get it. Supercuber says maybe compiler grouping. Oh, some. Whew. And if I could figure out how to spell precedence, I would be a billionaire. Okay. One type is more general than the other. Expected function pointer RS with a do these I was just about to say, should these all be static functions or but we need the self, right, in order to get the chunk and all that. All right. Well, Supercuber says that for syntax always scares me. Yeah, I think all they're saying is that they're expecting a something with two different lifetimes, right? The compiler versus the what's being passed in here, and instead what I gave it was this with no lifetime or an anonymous lifetime. There should be. I'll have to look that up. I am out of time, unfortunately, which is a shame. Rust pointer to not static function. What do they call them? They're not called member functions. Yeah, this is saying this, but it's expecting something different. Like this. That's if we want a pointer to it anonymized, but this is a calling bar, isn't it? Oh, the problem's in the type definition, Supercuber says. This needs to be not mutt compiler, but mutt compiler with a lifetime. Yeah. All right. Yeah, grouping is just mutt self, right? I mean, I don't want to start adding lifetimes on these things. All right. Well, I'm unfortunately going to have to end here. I'm going to take this out just for now. And what I can do is I can play with it a little bit. Let's comment this line out just for now so it actually builds. And then I can push this code up. Yeah, so we have 23 warnings. Git status, git add source, git commit, part way through chapter 17. And I'm just going to push this for now, and unfortunately going to call it a stream. And leave you guys there. All right, so next week I'm off at spring break. And the week after that, I'm going to leave myself hanging for a long time because we're going to work on One Night in the City, which is almost the last chapter, the second to last chapter. Although he did promise one more after Dark Elf Plaza. I think these are going to go quickly, though, because I peeked ahead a little bit, and it's mostly JSON code instead of actual coding code. And so maybe we'll finish this in a couple of days and we'll get right back to the parser. All right. Well, thank you everyone for hanging out with me. I'm sorry we're leaving things kind of up in the air. But I need to get going to work. So, yeah. Enjoy your weekend. Enjoy next week. I won't see you until Cal. Until the 25th. I will see you all on the 25th, and that's where we end things, unfortunately. All right. Take care, everyone.